Hello and welcome back to Math Class in Session, the Sine Law. Given any triangle ABC, doesn't have to be a right angle triangle, any triangle ABC, like this one for example, notice across from uppercase C, we have side lowercase c. Across from vertex uppercase A, we have side lowercase a. Across from vertex uppercase B, we have side lowercase b. Provided this convention is followed, the sine law states A over sine A equals B over sine B equals C over sine C. And the letters do not matter. It could be X over sine X. Sometimes it's convenient to flip all three of them, in which case we have sine A over A equals sine B over B equals sine C over C. You can't flip some of them, but you can flip all of them. Example, determine the length of side A. Use the sine law to find a side length. A, the one that's across from vertex A. Well, we could start by determining angle C, because it's easy. If you have two angles in a triangle, you also have the third one. Because it's 180 degrees, take away the other two, like this. Angle C is 180, subtract 30, subtract 48, which is 102 degrees. So we have angle C, it's 102 degrees. Step 2, set up a sine law application. This may be the hardest part. Remember, it's A over sine A equals B over sine B, so we could start with our unknown, A over sine of the angle opposite. So A over sine A, and in this case, because we know about C, we could say A over sine A equals C over sine C, and plug in the numbers. A over sine 30 equals 12 over sine 102. Notice the going across the triangle action. Multiplying the sine 30 and turning it into a decimal on a calculator. Do it yourself, confirm it for yourself. Let's do another example. Given a blurb of information, no diagram given. Given triangle PQR with angle Q is 44 degrees, Q lowercase is 73 centimeters, and P lowercase is 95 centimeters. What is the measure of angle P? Step 1, draw a sketch. So on this sketch, we'll put angle Q is 44, and lowercase q across from Q will be 73. Meanwhile, the side across from vertex B is 95 centimeters. Step 2, set up a sine law application. So if we seek angle P, we'll start with angle P in our sine law application by going sine P over P equals sine Q over Q. And plug in the numbers. Sine P over 95 equals sine of 44 over 73. Cross multiplying, doing some calculator work, we have sine P, and algebraically sin steps across the equal sign and becomes inverse sine, and we get angle P equals 64.7 from our calculator. A couple of words about this example. The sines of supplementary angles are equal. Confirm these for yourself. Sine 30 equals sine 150. Sine 80 equals sine 100. Sine 64.7 equals sine 115.3. Whenever two angles add up to 180 degrees, they've got the same sine. You can confirm this on a calculator. Now, each of these angles, 30 and 150, 80 and 100, 64.7 and 115.3, each of those will fit into a triangle. But the calculator, when asked for the angle whose sine is say 0.9040, will always give you the acute angle, when we don't know, but possibly the obtuse one might be the correct answer. So one way to help decide which angle is the correct angle is to observe a simple rule for triangles, which is as follows. The largest angle is opposite the longest side. The smallest angle is opposite the shortest side. Sometimes that helps. And sometimes there will be two possible solutions, like in the previous example. Moral of this story: use thought and use caution when you use your inverse sine function, because sometimes it doesn't tell the truth. Sometimes it might put the largest angle opposite not the longest side, for example. Now let's take a look at that example we just did. We were given this. We drew a sketch. We put the sides and the angle on. We set up a sine law application. We did this work. And we came to this and we said the inverse sine, angle P is the inverse sine of 0.9040. And here's the thing, it might be what the calculator said, 64.7, or it might be the supplement of that. And you just have to be suspicious. And now, compass directions. That's a compass rose, north, east, south, and west. So where is this other plane? If we are at this compass rose and there's another plane out there, north 30 degrees west, where will we sight it? That means go north and bend 30 degrees to the west. That's what north 30 degrees west means. How about east 50 degrees south? It means point east and then bend 50 degrees towards the south. West 42 degrees north. Head west and then bend upwards 42 degrees towards the north. These were used back in the day of the Titanic, for example, when you check the archives. Directions were expressed in this way. And northwest means halfway between north and west. So it means north 45 degrees west. Modern day headings and bearings are 3 digits long, a simple number that has 3 digits in it. And it's always measured from the north and then to the right in a clockwise direction. An example, a heading of 120. For example, if Pearson International Tower tells United Airlines to take up a heading of 120, that means fly straight north and then bend 120 degrees around to the right, like that. That's a direction that only has 3 digits in it. It's the same as east 30 degrees to the south. Let's do another one, a heading of 220. That means go north and then bend 220 degrees around. So we have to count 90, 180, 270 would be too much, so it must be in here somewhere. 220 degrees, and it's the same as south 40 degrees west. Because there's 40 degrees here, if this is 220 and this would be 180, well, this must be the other 40 here. Let's do a word problem. The light from a rotating offshore beacon can illuminate effectively up to a distance of 250 meters. A point on the shore is 500 meters from the beacon. From this point, the sight line to the beacon makes an angle of 20 degrees with the shoreline. What length of shoreline to the nearest meter is effectively illuminated by this beacon? Draw a diagram. There's the beacon, there's the shoreline, here's the point, and it makes the sight line to the beacon makes a 20-degree angle with the shoreline, and it's 500 meters away. Now, this beacon can only effectively illuminate up to 250 meters, so this point on the shoreline is never illuminated by the beacon because it's 500 meters away. However, there is some point along this shoreline where the beacon will illuminate. And so let's draw a line to that. And we know that that's 250 meters away. And along the shoreline at some point, it becomes 250 meters again, beyond which the beacon does not effectively illuminate. And so we have a diagram that looks like this. I see an isosceles triangle here. And this distance between these 2 points along the shoreline, this distance x, is the answer to the question, what length of shoreline to the nearest meter is effectively illuminated by the beacon? So the question has boiled down to, given the diagram, find x in meters. I've transferred it all, brought it all forward, and I labeled the vertices A, B, D, and C. And I put some angles in here. Because this is an isosceles triangle, I'm calling this angle theta, and I called this one beta. Now, in triangle ABC, in this triangle, the large triangle, ABC, the large triangle, we'll do a sine law application. Sine theta over 500 equals sine 20 over 250 in that large triangle. Multiply the 500 over, take your calculator, turn it into a decimal inverse sine function. Theta is 43.2 degrees. Theta, 43.2, which means that beta must be 180, take away 2 of those thetas. 180 take away 2 of those 43.2s leaves 93.6 for beta. And now focusing on the small triangle, in triangle ADC, the small triangle, we can now get x, because x over sine beta equals 250 over sine theta, and we know what theta is. It's 43.2. So x over sine 93.6 equals 250 over sine 43.2. And multiplying the sine over here with the 250 and doing some calculator work gives us x equals 364.5 meters. Therefore, that's how many meters of the shoreline can be illuminated.